This one doesn't involve any calculation. It's more like some description questions. All right. So let's have a look at that. This is page 1, June 15, 341. Okay, so for our case here, June 15, P41, we have this. Question number 4. Now, state for an oscillating body, what is meant by force frequency? This is something that we saw from the notes. Force frequency is the frequency at which an object is made to vibrate or oscillate. And then after that, what is the natural frequency of vibration? So natural frequency of vibration can be thought of as the frequency at which an object will oscillate after being given an initial disturbance. Rather than saying when given an initial disturbance, it will probably be more appropriate to say after being given an initial disturbance. Okay, you can say natural frequency of vibration is the frequency at which an object will oscillate after being given an initial disturbance. The marking scheme puts it another different way. They tell you it's the frequency at which object vibrates when free to do so. This sounds really weird. The frequency an object vibrates when free to do so. Okay, but there's another different answer that you can use. This one again is from the notes. This one is the frequency at which an object vibrates when no external force acts on it. This one is by far the most marking scheme appropriate answer. Okay, if you write this one, it will fit all kinds of questions that talk about natural frequency. Okay, frequency at which an object vibrates when no external force acts on it. It's already inside your notes also, if I'm not mistaken. In the first page, yeah, right? Yeah, it's already inside the notes. Okay, I mentioned to you that time there's actually 2 definitions. Either you use the first one or you either use the second one, right? I'm referring to this part of your notes. Okay, so that's for natural frequency of vibration. Now, next one we want to talk about is resonance. Okay, so resonance, we just went through it, is a phenomenon in which a system responds as maximum amplitude to an external driving force when the driving force frequency is equal to the natural frequency of the system. This is exactly what you saw from the notes, but you want to shorten it because it feels very, very long. You can do so. You can instead write it as this: maximum amplitude of vibration of oscillating body when the force frequency equals natural frequency of vibration. For some people, this one feels a lot easier to memorize. Okay, so either one, all right. Now, if you want to go to the next question, state and explain a situation where resonance is useful. Okay, so we went through some examples where resonance is useful and where it's not. So here they want a situation in which resonance is useful. Okay, the one that is actually written in pencil here talks about vibration of quartz or piezoelectric crystal at resonance to maximize amplitude of ultrasound waves produced. When you read it as it is right now, you probably do not know what are they talking about. This one is actually in another different A2 chapter that you will go through later on. It is under the chapter of medical imaging, where we talk about production of ultrasound waves. Okay, so this one, you will actually learn about this much later in a different chapter in medical imaging. Okay, so right now you probably don't know what this is talking about, but there's another separate answer which you can use and you should understand. That one is the one over here. You still say that vibration of water molecules in food at resonance that produce heat in the microwave oven. This one is accepted. Okay, so there's 2 answers. One answer is for much later. Another answer is something that you can readily understand. Okay, so this one should be fine. Okay, then if you're okay with this, then let me clear off some of the write things and scroll downwards. Okay, so the next one talks about in some situations, resonance should be avoided. State one such situation and suggest how the effects of resonance are reduced. Okay, so describe a situation where resonance should be avoided and how the effects of resonance are reduced. You could probably try and use the examples on the notes, but the marking scheme gives another separate example, which I wrote here. They tell you vibration and resonance of metal plates on a machine that can cause the metal plates to loosen. To avoid this, change the shape or area of the metal plate or the metal panel. Okay, now this one, if you read it as it is, it may not make much sense to you. So let me give you an example. What machine are they talking about? They could be talking about your washing machine, which you can see at your home. Now you see your washing machine looks like this, and there's usually a middle compartment here where you tend to put all your clothes in, right? All right. So when you switch on your washing machine tends to spin in one direction. Okay. So when your washing machine is spinning in one direction, it tends to throw your clothes, which are wet in the first place, up and down. Okay, so you can imagine if your clothes are inside your washing machine, you already switch it on, it's already wet with water inside, your washing machine starts to spin. So it's essentially throwing your wet clothes up and down. So this one produces an oscillating force. When your washing machine throws your wet clothes up and down, it produces an oscillating force at a certain frequency. Okay, so let's call this frequency your driving frequency. All right, so your washing machine by right should have its own natural frequency too. So let's call this Fn. Okay, so if let's just say you have the right combination of clothes, if you have the right combination of mass of clothes and right combination of turning speed, it will come to a case where your driving frequency is equals to your natural frequency. So what happens then is that your washing machine will start to vibrate uncontrollably because it's trying to vibrate with maximum amplitude. Okay, so when it tries to vibrate with maximum amplitude, you have to see that your washing machine is actually made out of metal plates fastened together. You see, you have one metal plate here, two metal plate here, three metal plates here, and then after there are some other metal plates behind it, right? So you have the fourth metal plate here, fifth metal plate here, right? So you have a lot of metal plates around your washing machine. When your washing machine is vibrating with maximum amplitude at resonance, your plates that are fastened to your washing machine could start to loosen. You see, your metal plates are fastened together to your washing machine by screws. Okay, so if your washing machine is now trying to vibrate with very large amplitude, it shakes a lot, the screws that are fastening your plate to your washing machine could start to loosen. So when your screws start to loosen, your metal plates start to loosen. So it will loosen and then it will fall off. Okay, that's what this first statement here is actually trying to tell you. Vibration and resonance of metal plates on a machine that can cause the metal plates to loosen. All right. So if you want to avoid a case where your driving frequency equals to natural frequency, what we'll say is that you just need to change the shape or area of your metal plate so that your natural frequency becomes a different value so that it doesn't come to a case where you have resonance. Okay. Now, this case where your washing machine achieves resonance is probably something that you may have encountered at some point at your home before, all right? you will notice that in some rare instances, your washing machine suddenly starts to vibrate violently, and then you have to immediately stop the washing machine, right? And then take off some of the clothes. That is your washing machine vibrating at resonance. Okay, if you don't stop your washing machine at that point where it's vibrating at resonance, your washing machine will actually start to break apart. I have a video of something like that just to show you what I mean. This is just an exaggerated case now, but it does show you what I mean by that. So let me just open it up.
Oh, it's about to rain, but
okay. So let me just share that. Okay, so here you should be able to see some sort of pulse video with a washing machine, right? So this guy actually put some sort of metal block inside, and then you go and switch on the washing machine. So you'll see what is the effect of throwing your mass up and down on the washing machine. So you see, the faster the guy spins the mass up and down, the more violently your washing machine will vibrate, right? So you see, the more it tends to vibrate, the more the plates around your washing machine will start to loosen up. Okay, so this is what I actually meant by the washing machine vibrating violently. Okay, see, the metal plates are all starting to loosen up. Okay, so I'll just let it run for another few seconds. Right, so yeah, this is an exaggerated example of what could happen at resonance. All your machine, the plates around it, start to come apart. Okay, so back to my worksheet. All right, so to avoid that, change the shape or area of the metal plate. That's all that you need to say. Okay. Or there's another answer here. They say place strengthening struts across the panel. What they mean by that is this. If this is your washing machine, sorry, if this is your washing machine, strengthening struts will be something like you place a bar right across the plates to prevent your plate from loosening outwards. Okay, and that's what we call by strengthening struts. You place some sort of bar across the plates in order to prevent it from coming out. Okay, so that one is what we mean by this. Okay, so page 1 is all right. Then we move on to page 29. Okay, so have a look at page 29. This is March 18 P42. Okay. Also question 4. Now explain what is meant by natural frequency of vibration of the system. This is something that we actually just did recently. The frequency at which a body will vibrate when there's no driving force acting on it, the frequency at which the body will vibrate when there's no resistive force acting on it. The marking scheme actually gave 2 variations of the answer. When no driving force acts on it, when no resistive force acts on it, it actually can be simplified to just one simple answer. Frequency at which object vibrates when no external force acts on it. Okay, it can be summarized as just this. That's why I said this answer previously was the best answer to use, because marking scheme always tends to give some variation of another. Here they say driving force, then another answer they say resistive force, but both are actually external forces, so might as well you simplify them. Okay, the other answer that I also gave you was natural frequency is the frequency at which the system oscillates after being given an initial disturbance. This one not so common now. All right, it's better to use this. Okay, now part B. You have a block of metal that is fixed to one end of a vertical spring. The other end of the spring is attached to an oscillator. So always look for keywords like this. Is there an oscillator in your system? So your spring is attached to an oscillator. Now they tell you the amplitude of oscillation of the oscillator is constant. The variation of amplitude x0 of the oscillations of the block with frequency f of the oscillations is as shown here in the diagram below. So the oscillator is making the metal block attached to the spring oscillate. What they've done here is that they measure the amplitude of oscillation with the corresponding frequencies, and you get the graph below here. This one, as I mentioned to you, is actually your resonance curve. Okay. So here they ask you what's the effect shown in the graph? Is resonance. Okay. It shows you where are you gonna get maximum amplitude and at what frequency. Okay. So the effect that you see there is resonance. Now state and explain whether the block is undergoing damped oscillation. So same thing as before. How do I know whether there's damping or not? I know that the peak is not infinitely high, thus the oscillation is damped. Okay. So that one is for that. Then for part C, state an example in which the effect shown in figure 4.2 is useful. What examples can you think of that tells you that resonance is useful? So you can fall back to the very simple example where we say you use it in microwave ovens to heat food. Okay. And then after that, there are some other few other answer choices. You can say is in quartz crystal to produce ultrasound. This one will still be relevant to you because this one is under medical imaging. You could use this. Now in quartz crystal to keep timing, in tuning circuits of radios and televisions, in MRI to produce image scans of the body. You can just think of this as not in syllabus, no? Okay. Because the things that they describe here have something to do with some other chapters that used to be inside your syllabus, but it's now no longer inside your 2022 syllabus. Okay. So to make your life easier, don't need to bother about this now. Okay. Just make sure you know the first two. That one will be sufficient. Okay. So this one I will just say not in syllabus anymore. Okay, so that one is okay. Then I move on to page 21. I'm at 29 just now. So I move on to page 21. Okay, yeah, this one talks about damping again. So have a look at page 21. June 2017 P41. Question 2. Right. So if you read this question on page 21, we mentioned here that you have a bar magnet of mass 180 grams that's suspended from the free end of a spring. The magnet hangs so that one pole of the magnet is near the center of a coil of wire. The coil is connected in series with a resistor and a switch, where the switch is now open. The magnet is displaced vertically and then allowed to oscillate with one pole remaining inside the coil. The other pole remains outside the coil. At time t equals to 0, the magnet is oscillating freely as it passes through the equilibrium position. At time t equals to 3 seconds, the switch in the circuit is closed. And then the variation with time t or the vertical displacement y of the magnet is shown in the graph below. Okay, so simply put, your magnet is here, you displace it, you let it oscillate up and down, and then after that, they measure the displacement of your magnet with respect to time as shown in the graph below. Okay, this is what you are seeing right over here. Now, there's one thing that you can actually kind of see from here. From here to here, there's actually no damping because you can see that your amplitude is constant. Okay, but then after that, from here to here, you actually have damping because you look at how your amplitude is changing, it's actually decreasing. So we know there's damping here. Okay, so that's one of the key things that you can actually see from this part of your graph. One part has damping, one part has no damping. Okay, so if you go to the next page that asks you to find out what is the frequency or oscillation of your magnet, find out two significant figures. So frequency is actually number of oscillations over total time. So you can actually just read from your graph. If I have 7 oscillations, what is the time taken for 7 oscillations? This is 1, 2, 3, 4, 5, 6, 7. Okay. 1, 2, 3, 4, 5, 6, 7. Yeah. So this one is how I found my frequency by taking the number of oscillations divided by your total time. But I think there's an easier way for you to do this now because you can actually just, there's no need to do it the way I did it. You can clearly see that this is actually one period. Your period is actually 1 divided by 5 is 0.2. Your period is actually 1.2 seconds. So frequency is 1 over 1.2. Giving you the answer that you're seeing right over here. 1 divided by 1.2 is 0.83 hertz. Okay. You could have easily just done this rather than what I just did in the screen here. Okay, you can just done this rather than what I wrote in the work solutions. All right. So that's for A. Okay, B. B is asking you to state whether closing the switch gives rise to light, heavy, or critical damping. Okay. Now, just now I mentioned to you that this part here has no damping, and then subsequently this part here has damping. Now, coincidentally, when you start to have damping is where you actually close the switch. You see, they told you that at time 3 equals to 3 seconds, the switch is closed. So at this point here, your switch was closed. That in effect caused your amplitude to drop. Okay. So here the question really just wants you to tell them, is it light, heavy, or critical damping? Okay. So one of the characteristics of damping just now, I did mention to you, light damping must always have oscillation maintained about the equilibrium as the oscillations gradually stop. Critical and heavy damping will just go back straight to equilibrium. They won't keep oscillating. So here, looking at the graph, you will see that oscillation is actually still maintained about the equilibrium position as the amplitude gradually goes to 0, isn't it? It doesn't straight away go to 0. Instead, it just continues oscillating while the amplitude gradually goes to 0. So this one is confirmed to be light damping. Okay. Right. So this one is light damping. Okay. Since oscillation is still maintained. All right. You can still see oscillation. So it's light damping while the amplitude drops. Okay. Right. So that is for part B. Now for C. Again, let me clear off the drawing. So for C, calculate the change in energy delta E or oscillation of the magnets between 2.7 seconds to 7.5 seconds. Explain your working. All right. So this one's for some very weird reason is worth 6 marks. It is way over half your question marks, typical question marks, sorry. So they want you to find the change in energy or oscillations between the two timings here, 2.7 and 7.5. So when you're talking about energy, you can always just fall back to the total energy equation, which is this one. ET is half m omega square x naught square. Okay, so let's have a look at 2.7 and 7.5. 2.7 seconds would be here. This is where t is 2.7 seconds. Then at 7.5, you will be here. This is where t is 7.5 seconds. Okay, so from here, what you really just want to do is you find the corresponding amplitudes at these two timings. X naught would be 1.5 centimeter for t equals to 0.7, for t equals to 2.7 seconds. And then x naught will be equals to 0.75 centimeter for t equals to 7.5 seconds. Okay, so these are the two timings and the two respective amplitudes. From there, you can actually now start to find out the energy loss. Okay, you take the difference between the two. So here, you can actually just say delta E is E1 minus E2, giving you 4.16 times 10 power minus 4 joules. Okay. You could try to write everything out combined together, but you'll be very, very long. I mean, if let's just say if you wanted to do it like this, let me just illustrate to you what I mean. You wanted to say that delta E is E1 minus E2, which in turn will be half m omega square x naught 1 square minus half m omega square x naught 2 square, in turn giving you half m omega square x naught 1, x naught 1 square minus x naught 2 square. You probably could do so, okay? No issues on that. You just get something like this. Omega is, yeah, don't forget to change your omega. Omega is actually 2 pi f square here, all right? Because you do not know the omega in the first place, do you? Actually, you don't. Yeah, you don't know omega. Okay, you would just use 2 pi f because you already found out the frequency here. You see in the first part of your question, part A, you've already found out frequency as 0.83. So you might as well just use omega as 2 pi f. Okay, so this one, let me just erase it a little. 2 pi f square, then x naught 1 square minus x naught 2 square. Right, so then this one becomes 4 pi square times 0.83 square times with 0.015 square minus with 0.0075 square. In the end, giving you 4.16 times 10 power minus 4 joules. Okay, you could do it like this now. If you wanted to, then this one will be worth 6 marks. Okay, but as I mentioned to you towards the end of the last week's lesson, sometimes it may be better to just write everything out separately and then show the relevant equations separately, because you never know, maybe during the process in which you sub in your values, you somehow substituted in the wrong values, or you forgot to square one term, so the examiners don't know whether do you really know the equation. So in the absence of any other evidence, they will just assume that you do not know and penalize you, right? So that was what I mentioned towards the end of the last lesson. So it might be better for you to show those things separately, like what you have right over here. This one is showing everything separately so that you can get the marks individually, just in case you make a mistake somewhere. Okay, but if you're really confident and you know that you're very careful, you can just straight away show this now. Okay, so it's really up to you. Okay, but for me, if I see if it were me, like if I'm short of time, I'll straight away do the ones on the right over here. Okay, if I notice that in the exam I'm short of time, I'll straight away just do this. Okay, all right. Okay, so maybe you want to do page 24 as your homework, okay, or practice. 24 is actually very similar to something we've just done, so I think this one I'll just skip. This one is page 62. Okay, now the defining equation of simple harmonic motion is A equals to negative omega square x. State the significance of the minus sign inside the equation. All right, so we've done this quite a fair bit already, so many times, so we should know that the negative sign actually just means that acceleration and displacement are always in opposite directions. Okay, so this one is pretty straightforward. Now part B is the one that's a bit different. Okay, so what is actually happening for this particular question? Let me just zoom it in for you. Is this right here? They mentioned to you that a trolley rests on a bench. Two identical stretch springs are attached to the trolley as shown in the figure. The other end of the spring is attached to a fixed support. The unstretched length of each spring is 12 centimeter. The spring constant of each spring is 8 Newton per meter. When the trolley is in equilibrium, the length of each spring is 18 centimeter. So here they then mention that the trolley is displaced 4.8 centimeter to one side and then release. Assume that the resistive forces on the trolley are negligible. Okay, so in our case here, this one was the diagram that you're seeing here is a case where the trolley was in equilibrium, it's not moving, and the length of each of the spring was 18 centimeter. So the thing was that they told you that the original, rather than saying this the original, I think it's better to say the unstretched length. They initially told you that the unstretched length of your spring is actually 12 centimeter. Okay, so at that time the question mentioned that you displace your trolley 4.8 centimeter to one side before releasing it. So if you displace it towards the right, for example, that would mean that this length would be having a decrease of 4.8 centimeter, and then this length here would be increasing by 4.8 centimeter. Okay, so what you're interested to know is the extension, or rather the change in length that is occurring for both of these springs. You have this spring, let's call this spring 1 with spring const, let's call this spring 1. This is number 1, and then the other one is this spring, let's call this spring number 2. Okay, so what you're interested to know is what is the force acting on the trolley right in the middle here. Okay, so but before we go through that, let's just find out what is the extension or rather the change in length for each of the individual springs. So you are supposed to find out what is delta x1 here. Okay, maybe this one I eliminate. You're supposed to find out what is delta x1 here, and then what is delta x2 here, the new change in length, or rather the new extension. So for our case, we know that delta x1 is going to be 18 plus with 4.8 minus of the original length. This one will give us 18 plus 4.8 minus 4, giving us 10.8 centimeter. Then delta x2 would be 18 minus 4.8 minus 12, giving us 18 minus 4.8 minus 12. Am I doing this correctly? 18 plus 4.8 minus 12 is 10.8. 18 minus 4.8 minus 12 is 1.2 centimeter. Okay, so the thing here to note is that this one is actually still considered to be extension of your spring. This one is also considered to be extension of your spring. So an easy way to look at it would be to think of it as this way. If for spring number 1, the length was 18 centimeter, now this one, the length is now 18 plus 4.8, giving you 22.8 centimeter. This is obviously extension here, where the extension is 10.8 centimeter. But if you look at the other, sorry, this one was 12 centimeter. This is the original unstretched length. Okay. If you look at the other spring, the original unstretched length is also 12 centimeter, but the new length right now is actually 18 minus 4.8, giving you 13.2 centimeter, where your extension is therefore 1.2 centimeter. So you see both these cases, if you compare with respect to your original length, the unstretched length of 12 centimeter, you are really still getting extension because your final length is still longer than the unstretched one. Okay, so the mistake I made last week was that I thought that the length decreased because it was minus 4.8. So I had mistakenly assumed that the spring was under compression. If you recall what I did last week, I mentioned to you that the spring force due to 1 will actually be, spring 1 will be here, and then the spring force due to 2 would be here, right? So this is actually wrong. This one is assuming that the spring was under compression. I had mistakenly assumed that if your length decrease here, you're actually compressing the spring. So because you're compressing the spring pushes back on the trolley. That's why your force is towards the left. This is actually not true. Okay, this was the mistake that I made last week. Your case here is that your spring force for spring 2 is actually supposed to be here because your spring is still under extension, just that your extension is less. Okay, so let me just make a note here. This one, force 1 is due to, let me make a note here. So your delta x1 is still extension. Your delta x2 is still extension. So in both cases where the springs are extension, your spring 1 will try to pull your trolley to the left. Your spring 2 will try to pull the trolley to the right. That's why the force direction is opposite now. Okay, that's the correct way to interpret this diagram now. So here they ask you, show that the resultant force acting on the trolley at the moment of release is 0.77 Newton. So here, if I wanted to find out the F net, I can just say is F1 minus F2. Because you see this one, X1 is the larger value. Therefore, F1 is larger because your extension for spring 1 is larger than 1.2. This one is definitely going to be the larger one. F1 is definitely going to be the larger one. This one is smaller. Therefore, F2 is smaller. That's why I say F1 minus F2. So spring force is K times delta X. If you remember this from last time you do your AS, let me write this out properly for you. F is K delta X. Okay. So here what you have is actually this one. K delta X1 minus K delta X2. I'm gonna get the spring constant as 8. Your extension number 1 is, for spring 1 is 0.108 minus extension for 2 is 0.012. So eventually you get 0.108 minus 0.012 times 8. You're gonna get 0.768 Newton, which rounding up to 2SF gives you 0.77 Newton. Okay. Right. So this is the correct way to interpret your question. All right. Okay. So this one is for part 1. We move on to part 2 a little. Let me just have a look at the answer for part 2. Okay. So I'm just going to clear out the diagram, the writings on the board. Okay. Now, the mass of the trolley is 250 grams. Calculate the maximum acceleration A of the trolley. So here, you just use F net equals to MA because you already know what is the resultant force. You already know the mass. You can work out what is your acceleration. This is the maximum possible acceleration for your trolley here. You are not really going to be using A equals to negative omega square X, where A max is actually omega X naught here, because you don't even know what is omega in the first place. They didn't tell you any information about omega. Or rather, they didn't tell you any information about the period or frequency. If you had known 2 pi over what's the period, you can use this. Or if you had known the frequency, you can use this. Okay. Right. So, but here you cannot use this one. All right. You need to use a different one, which is F net equals to MA. Okay. Now, the third part of your question is asking you, use your answer in 2 to determine the period T of the subsequent oscillations. So it's from here, you want to find out period. Okay. So if you know that A max is actually omega square X naught from here, you want to change out omega so that it becomes 2 pi over T squared multiplied with X naught. Okay, so your A max was 3.08 equals to 2 pi over T squared times 4.8 times 10 power minus 2. So your period is going to be 0.784 seconds. Okay, so while they did not give you your period initially, they now want you to find out your period. Okay, so that's the way to do this. Okay, now for your amplitude, 4.8 times 10 power minus 2 is actually from the fact that you actually displace your trolley 4.8 centimeter in the first place. Okay, so that time I mentioned to you, whatever initial displacement you give your system, that one will be the maximum possible amplitude. It will never be larger. It can only get smaller from there if you have damping. Okay, but in your case now, you just use the value 4.8 because they want you to use the maximum possible amplitude. Okay, so that you can get A max. Okay, so this is the period. Okay, the last part is on a state and explain question. So here they mentioned this to you, all right? Let me just zoom this one in. Here they mentioned that the experiment is repeated with an initial displacement of the trolley of 2.4 centimeter. The one before this was 4.8 centimeter. The one that you used before this was 4.8 centimeter. Now you're changing it to 2.4 centimeter. State and explain the effect, if any, of this change on the period of oscillation of the trolley. Okay, so by right, the period should actually remain unchanged, because remember last time I mentioned to you, when you have a free oscillation system like this, I give you the example of your pendulum board. If you initially give it an initial displacement of say 5 centimeter, or if you use back the same pendulum board and you give it an even larger displacement of say 10 centimeter, and you release both of them, both of the systems will oscillate, correct? But the period will remain the same. If say the period was say 5 seconds, this one the period will also be 5 seconds. Okay, so the only thing that would have changed with you having a larger amplitude was that your speed increased only. Okay, so that was the thing that I mentioned to you last time when I was describing to you free oscillation. You changing the amplitude or you changing your initial displacement doesn't change the period. It actually should remain the same. The only difference then was that your speed should have increased to cover a larger distance in the same time. Okay, because if you have a larger displacement, or rather a larger amplitude, you will actually be moving much larger distance. But to have a period of 5 seconds, the same as before, you will need to move faster. Okay, so here the period is unchanged, but you still have to kind of explain why do you say that it is actually unchanged. Okay, so what you could say is something like this. You could say that the initial displacement is half, so your resultant force and hence acceleration is half. Your maximum displacement is also half, therefore your period remains unchanged. Okay, so that's what they want you to explain here. You have to make mention that your displacement is half here, so your resultant force and hence acceleration is half. This one is actually kind of saying that you move slower than before. Maybe I better summarize this. In layman terms, the last two, the two statements in orange here actually means this. You move slower than before to cover a smaller distance so that the period remains the same. This one, you move slower than before to cover a shorter distance. Therefore, period remains the same. Okay, that's one way you can kind of interpret this statement in orange here. Okay, you are now moving slower because your acceleration is half. You're also covering a shorter distance because your maximum displacement is also half. So both of them contribute to you having the same period. Okay.